What if I told you that right now something moving at 55 kilometers per second is crossing our solar system, so fast it would blow past the distance from New York to Los Angeles in under 2 minutes? 3I Atlas arrived in July 2025, our third confirmed visitor from interstellar space, and is on a trajectory that will carry it safely past Earth at roughly 300 million kilometers. But here's what keeps me up at night. Speed changes everything in cosmic collisions. Energy scales with the square of velocity, so a small wandering nucleus can be more destructive than an object 10 times larger. What if the orbit calculations were off by just a few kilometers? What if this ancient wanderer, forged around a distant star billions of years ago, were aimed straight at Earth? For now, 3I Atlas is safe, while planetary defense is learning to live with uncertainty. Every 2 years, the world runs a crisis rehearsal, a hypothetical several hundred-meter asteroid, a 72% impact probability in 14 years, a risk corridor stretching from North America to southern Europe and North Africa. Then the object swings too close to the Sun, and we enter a 7-month observational blind spot. This isn't a movie. It's training so that on a real day X we don't start from scratch. In scenarios like these, the first question is what we actually know: size, mass, composition, precise orbit. One path is reconnaissance. Send a spacecraft to narrow the uncertainties. Another is deflection. Nudge the body off course as DART did, measuring a real change in an asteroid moon's orbit for the first time. But that takes time. Which is why humanity is building earlier eyes. The infrared NEO surveyor and the wide-field surveys of the Vera Rubin Observatory should markedly increase detections, including fast interstellar visitors. The planet already carries warnings. Small bodies frequently enter the atmosphere. One in January 2024 flared over Europe, predicted in advance. Another burned up harmlessly over Siberia, leaving only a light show. Small events remind us of a big rule. Fast-moving comets punch above their weight, and speed is what makes them dangerous. Now to 3I Atlas itself. Its frames arrive in neat digital packets, each time-stamped and calibrated. Against the steady stars, a faint point shifts, at first only in side-by-side images taken hours and days apart. The trajectory is hyperbolic, born beyond our system, and current calculations steer it past Earth with a comfortable margin. But specialists focus not only on this guest, but on the class of such guests. Modern estimates suggest interstellar wanderers pass through our system far more often than we manage to spot them. Which means the question isn't if, but when one ends up on an inconvenient orbit. Tonight we'll map that inconvenient when. We'll see how humanity's choices change if 3I Atlas were to enter an impact corridor, from the first weeks of uncertainty in a solar blind spot to the decision to observe, deflect, or evacuate. We'll trace how a small rock, moving faster than any human-made craft, can set off a chain of events stretching across decades: diplomacy and joint missions, strains on economies and energy systems, and above all, a race against time. And we'll start with fundamentals, the physics of impact. Speed is the prime multiplier. Even a kilometre of rock at a typical 20 kilometres per second carries tens of thousands of megatons of energy. At interstellar speeds, the same mass climbs higher still. The Chicxulub story teaches two things. Not just size and speed matter, but also where you hit and how much fine dust is lofted into the stratosphere, dimming light and heat for years. If so much hinged on a shallow carbonate shelf 66 million years ago, today's risk map has to be layered: speed, angle, composition, target. Next comes the practical playbook. What do we do in the first 72 hours after the orbit shifts into the hazard corridor? Who green-lights a scout mission? How do we book windows for a deflection attempt? Where do evacuation lines run if projections point to the North Atlantic, the Mediterranean, or the Sahara? Where does panic end and work begin? If you enjoy questions that unfold slowly like this one, I'd be grateful for a like or a subscribe. It helps this quiet little signal reach other curious minds. No pressure, just an invitation to follow a faint trail that sometimes leads somewhere unexpected. Make yourself comfortable. We're beginning our dive into this documentary film for sleep. An interstellar comet 3 kilometers across, arriving at 55 kilometers per second, would release roughly 3 million megatons of energy, enough to excavate a 60 to 90 kilometer crater and loft vast amounts of dust into the stratosphere. The chance of such an impact in any given year remains vanishingly small. Current estimates suggest kilometre-scale interstellar objects may collide with Earth roughly once every 10 to 100 million years. But probability and possibility are different concepts. The question we're considering is not whether such an impact will occur, but what happens if it does. The answer shapes our thinking about detection systems, deflection technologies, and the broader task of planetary defence. For now, 3i Atlas continues its peaceful journey through the inner solar system. It will reach perihelion at about 1.4 astronomical units from the Sun on October 30th, 2025, and then begin a long trip back to interstellar space. Telescopes around the world will track its motion, measuring composition and behaviour as solar heating activates its surface. We will learn something new about materials that formed around other stars billions of years ago. But we also pursue another line of inquiry. In the precise mathematics of celestial mechanics and impact physics, and in the painstaking work of sky surveys and threat assessment, we find tools to recognise the moment when a visitor from the stars may be more than just a scientific curiosity. The universe contains many wandering bodies, and not all of them will pass quietly by. We are preparing for those that won't. Part 2. The last time a large object struck. The evidence is hidden in a thin layer of clay found worldwide. In some places it's only a few centimetres thick. In others it forms a distinct dark band between limestone beds. Wherever it appears, this boundary marks the same moment in Earth's history. The end of the Cretaceous, 66 million years ago, when an object from space transformed the planet and ended the age of dinosaurs. The Chicxulub crater spans 150 to 180 kilometers on today's Yucatan Peninsula in Mexico. Most of it lies buried beneath younger sediments, but gravity surveys and drilling campaigns have mapped its structure in detail. The crater's size points to an object about 10 to 12 kilometers across, moving at 20 to 30 kilometers per second, when it struck a shallow carbonate platform that covered the region in the late Cretaceous. The impact energy approached 100 million megatons of TNT. For comparison, that is about 6,600 times more powerful than the largest nuclear weapon ever tested. But a single energy number tells only part of the story. The devastation was determined by where that energy went and how long its effects persisted in Earth's atmosphere and climate system. When the object struck, it vaporized itself in enormous volumes of target rock. A crater formed within minutes, ejecting molten debris on ballistic arcs around the globe. Some of that material returned within hours, heating the air and igniting forests across entire continents. Larger fragments fell for days to weeks, creating a secondary bombardment that prolonged the period of atmospheric heating. The most significant long-term effect came from finer material that remained suspended in the stratosphere for years to decades. Recent research has reshaped our understanding of this atmospheric load and its consequences for life on Earth. In 2023, researchers at the University of Texas analysed cores from North Dakota that preserve an exceptionally detailed record of the impact boundary. The analysis revealed abundant fine silicate dust particles 0.8 to 8 micrometers in size. These particles appear to have lingered in the atmosphere for 15 to 20 years after the impact, with peak concentrations lasting for 5 to 8 years. In the first 2 years, the dust load was so severe that photosynthesis almost completely shut down on a global scale. This finding was a major shift in the scientific understanding of the Chicxulub extinction. Earlier models mainly tied the consequences to sulfur aerosols produced by vaporization of sulfate-rich rocks, or soot from impact-triggered fires. Both factors cooled the climate and reduced sunlight reaching the surface. But fine silicate dust proved no less important, and it stayed aloft far longer than previously assumed. The implications reach well beyond academic paleontology. If fine dust can persist in the atmosphere for decades after a large impact, the threshold for triggering serious climate effects may be lower than thought. Even a smaller object could inject enough dust into the stratosphere to disrupt photosynthesis for multiple seasons. That could potentially drive ecosystem collapse even without the sulfate-rich geology that amplified Chicxulub's effects. Geological data also point to other impact consequences that rippled through Earth's interconnected systems. Enormous tsunamis raced across shallow seas, leaving chaotic deposits of mixed rocks and fossils. Acid rain produced by sulfur and nitrogen compounds formed in the impact fireball altered ocean chemistry for thousands of years. The combination of instantaneous thermal effects, prolonged darkness, and chemical changes created what researchers now call the Chicxulub impact winter. This ancient catastrophe remains our best natural laboratory for understanding how impacts affect planetary systems. The boundary layer preserves evidence of not only immediate destruction but also long-term recovery. Life ultimately rebounded, but restoring pre-impact biodiversity took millions of years. The mammals that survived continued to diversify and eventually gave rise to human civilization. But the path from impact to recovery was neither fast nor simple. Chicxulub's lessons shape modern understanding of asteroid and comet hazards. We now know that atmospheric effects can extend far beyond the immediate strike region. We also know that relatively modest amounts of fine dust can have disproportionate climate impact if they reach the stratosphere, and persist not for months, but for years. This understanding also informs modern attempts to model the effects of smaller impacts. Simulations show that objects just 500 meters to 1 kilometer in size can cause regional climate effects if they strike at high speed and loft sufficient dust into the upper atmosphere. The exact threshold depends on many factors, including impact velocity, target geology, and the size distribution of ejected particles. Chicxulub also demonstrates the importance of impact angle and target type. The Mexican impact came in at about 60 degrees to vertical, which was nearly optimal for maximizing both the amount of vaporized rock and the efficiency of ejecting debris into the stratosphere. A more glancing strike could have made a larger crater, but lofted less material into the sky. A steeper impact could have penetrated more deeply but produced a more localized ejector pattern. Perhaps most importantly, the Chicxulub boundary reminds us that large impacts are not abstract possibilities, but documented events in Earth's history. The crater exists. The boundary layer exists. The extinction is recorded in fossils found worldwide. What happened 66 million years ago can happen again, though timescales suggest that in the foreseeable future we are more likely to face smaller, yet still significant impacts. By considering scenarios with objects like 3I Atlas, we bring these deep time lessons forward. The physics of high-speed collisions obeys predictable laws. The climate system responds to atmospheric dust loading in ways we can model and anticipate. The biosphere shows remarkable resilience on geological timescales. But that resilience has limits and operates on times far longer than the span of human civilization. The Cretaceous-Paleogene boundary marks not only an extinction event, it represents a transition from one world to another, orchestrated by a visitor from space that arrived at a most inopportune moment. We study that transition not to dwell on ancient catastrophes, but to better grasp the forces that could shape our own future. Part 3. Anatomy of a Cosmic Rock. The mathematics of destruction begins with a simple formula. Kinetic energy equals 1/2 the mass times the square of velocity. This relationship, fundamental to all high-speed impacts, explains why comets arriving from interstellar space pose such significant threats despite their relatively modest sizes. Speed dominates the energy budget and interstellar wanderers arrive fast. Consider the basic physics governing these encounters. A typical stony main belt asteroid has a density around 2.6 grams per cubic centimetre, comparable to granite or concrete. These objects follow elliptical orbits that bring them into the inner solar system at average speeds of 17 to 23 kilometers per second, where they cross Earth's path. Their velocities reflect a balance between gravitational acceleration toward the Sun and the orbital motion inherited from their origin in the asteroid belt. Comets follow a different pattern. Most long-period comets come from the Oort cloud, a spherical shell of icy debris extending to roughly 50,000 astronomical units from the Sun. When gravitational perturbations nudge these objects inward, they fall on nearly parabolic trajectories, accelerating as they enter the inner solar system. By the time they cross Earth's orbit, they typically move at 45 to 65 kilometers per second. But interstellar objects like Oumuamua and 3I Atlas arrive at even higher speeds. They spend millions or billions of years travelling through space unbound to any star. When they enter our system, they follow hyperbolic paths, fly past the Sun, and head back into interstellar space. Their velocities at Earth's distance from the Sun usually range from 45 to 72 kilometers per second, depending on approach angle and the Sun's gravitational focusing. Density differences between asteroids and comets also affect impact calculations. Cometary nuclei are loose aggregates of ice, rock, and organics, with densities from 0.4 to 0.8 grams per cubic centimetre, about as dense as fresh snow or pumice. This lower density partly offsets their higher speed, but the velocity squared term in the energy formula ensures that comets still deliver a far more powerful blow than same-size asteroids. Let's run a few examples. A 1-kilometre stony asteroid striking Earth at 20 kilometers per second would release about 65,000 megatons of kinetic energy. Increase that object to comet-like density and interstellar speed, and the energy jumps to roughly 114,000 megatons. The 75% increase is entirely due to the higher impact velocity. Now consider a smaller interstellar object. A 500-metre cometary nucleus arriving at 55 kilometers per second would release about 14,000 megatons. That is comparable to a 700-metre stony asteroid at typical Earth encounter speeds. Even Oumuamua, with estimated dimensions around 100 by 30 by 30 metres, would have delivered about 190 megatons in a direct hit on Earth. That is almost 20 times the energy of the 1908 Tunguska event, which destroyed 2,000 square kilometres of Siberian forest. The energy scaling climbs dramatically from there. A 3-kilometre interstellar comet would release about 3.1 million megatons, approaching the energy range estimated for the Chicxulub impact that ended the dinosaurs. A hypothetical 6-kilometre interstellar object would deliver nearly 20 million megatons, firmly in the realm of mass extinction events. These energy estimates provide a foundation for understanding impact outcomes, but turning energy into real-world effects requires additional factors. Impact angle plays a decisive role in how energy is distributed. Most impacts occur at 30 to 60 degrees to vertical, with 45 degrees the most probable by simple geometry. Shallow strikes produce different damage patterns than steep ones. A grazing impact at 15 to 30 degrees tends to form an elongated crater and distribute ejecta in a characteristic butterfly pattern, downrange from the impact point. The impactor can also skip or fragment while passing through the atmosphere, creating multiple strike points along its path. By contrast, a steep impact concentrates more energy into a smaller area and typically excavates a deeper, more circular crater. The size of the resulting crater depends on the impactor's energy and the target material's properties. A rough rule of thumb is that craters span 10 to 20 times the diameter of the impactor, though this ratio varies significantly with velocity and geology. A 1 kilometer object typically creates a 15 to 20 kilometer crater. A 3 kilometer impactor can dig a 60 to 90 kilometer crater. But not all impacts make craters. Smaller objects, generally below a few hundred meters across, often break apart in the atmosphere before reaching the ground. The resulting airburst can still cause serious damage over a large area via shock waves and thermal radiation, but without the deep excavation and mass ejector production characteristic of a surface strike. The transition between airburst and crater formation depends on size, speed, density, and internal strength. Weakly bound cometary nuclei tend to fragment more readily than solid metallic asteroids. A 100-meter iron asteroid may survive atmospheric entry intact, whereas a 500-meter comet nucleus may fail at high altitude. This variability makes it difficult to predict impact outcomes precisely without detailed knowledge of an object's composition and structure. Passage through the atmosphere adds another layer of complexity. Objects entering at interstellar speeds experience enormous dynamic pressures as they plough into denser air. The leading surface heats to thousands of degrees, creating a glowing plasma sheath visible for hundreds of kilometers. Pressure differences between the front and rear surfaces can tear weak objects apart, sometimes explosively. These physical processes shape final outcomes in ways that pure energy calculations cannot capture. One large impactor poses different hazards than the same mass distributed among many smaller fragments. Surface impacts generate different secondary effects than high-altitude airbursts. Ocean strikes generate tsunamis but less atmospheric dust, whereas continental strikes favour dust production over water displacement. Understanding these nuances becomes critical when modelling the potential effects of specific objects like 3 Atlas. The energy released by a hypothetical impact provides a starting point for analysis, but details of crater formation, atmospheric injection, and secondary effects determine whether the result is a regional catastrophe or a global one. Physics remains consistent across all scales. Mass, velocity, and the basic conservation laws govern every collision between objects in space. But the expression of these principles through Earth's complex systems creates a rich variety of possible outcomes. We map these possibilities not to revel in destruction, but to better understand the forces at work when worlds collide. Part 4. If 3I Atlas came close, imagine 3I Atlas on a different trajectory, not 270 million kilometers from Earth, but close enough to be seen with the naked eye. The math of comet brightness depends on both distance to the Sun and distance to Earth, modified by the level of activity as solar heating blows dust and gas off the nucleus. The baseline relation follows a well-established formula. Apparent magnitude equals absolute magnitude plus 5 times the logarithm of the distance to Earth, plus 2.5 times the activity index times the logarithm of the distance to the Sun. For most comets, the activity index lies between 2 and 5, with larger values indicating more vigorous gas and dust release as the nucleus approaches the Sun. But this standard calculation misses one of the most striking effects in comet observing: forward phase scattering. When Earth lies nearly on the line between the Sun and the comet, light scattered by dust in the coma and tail can produce dramatic brightening. The effect is like looking toward the Sun through a cloud of fine particles, where individual grains invisible in normal conditions suddenly flare with reflected light. The most famous recent example occurred in 2007 with Comet McNaught, designated C/2006 P1. During its pass by the Sun, forward scattering boosted its magnitude to -5 to -5.5, making it visible in daylight for observers in the southern hemisphere. The comet's dust tail stretched 35 degrees across the sky, creating one of the most spectacular celestial displays of the modern era. McNaught's performance shows what becomes possible when a sufficiently large comet nucleus approaches the Sun under ideal geometry. The nucleus was estimated at roughly 25 kilometers across, much larger than the likely size of 3I Atlas. But even a smaller nucleus can put on an impressive show under favourable circumstances. Recall Comet Hale-Bopp, which reached magnitude -1 during its 1997 outburst and remained visible to the naked eye for more than 18 months. Its exceptional longevity was explained by its massive nucleus, estimated at 40 to 60 kilometers in diameter. That size meant vast reservoirs of ice and dust continued to be released long after perihelion. But Hale-Bopp never came especially close to Earth, maintaining a distance of about 1.3 astronomical units at closest approach. Now imagine 3I Atlas on a hypothetical trajectory bringing it much closer, perhaps 0.1 astronomical units, or roughly 15 million kilometers. This is about 40 times closer than the Moon, deep within the orbits of some artificial satellites. At such a distance, even a modest nucleus a few kilometers across could become a spectacle. Forward scattering would likely dominate the brightness calculation. If the geometry cooperated, placing Earth almost between the Sun and the approaching comet, 3I Atlas would easily reach negative magnitudes and become visible in daylight. The exact brightness would depend on nucleus size, activity level, and dust production rate, all of which remain uncertain for this object. The comet's appearance would change rapidly as it approached over weeks or months. At first it might appear as a modest telescopic object, perhaps magnitude 8 to 10, visible only to experienced observers with good equipment. As it drew nearer and solar heating increased, the coma would expand and brighten. A tail would begin to form, at first only a faint elongation visible in long exposure images. But as the three-eyed Atlas came as close as possible to Earth, the tail structure would become ever more dramatic. Comets usually develop two distinct tails with different characteristics. The dust tail looks yellowish-white and gently curves away from the Sun as radiation pressure pushes particles onto curving trajectories. The ion tail glows blue-green due to excited gas molecules and points almost directly away from the Sun, shaped by the solar wind's magnetic field. During a close pass, both tails would be visible to the unaided eye. The dust tail could span 10 to 20 degrees of sky, creating a broad fan dominating the twilight. The ion tail could stretch even farther, appearing as a narrow blue-green band across the heavens. Night-to-night changes would be easy to notice as the comet's motion and shifting solar wind conditions reshaped the tail structures. Some comets also develop sodium tails, yellow in appearance and extending millions of kilometers. They form when solar radiation breaks down dust particles and releases sodium atoms that glow at specific wavelengths. A sodium tail often looks separate from the dust and ion tails, adding a third component to the comet's impressive appearance. Photography would capture details invisible to the eye. Long exposures could reveal intricate structure within the coma, including jets and fans as individual regions of the nucleus activate. The tail would show elaborate knots and streamers as solar wind magnetic field lines interact with the ion tail. Some observers might spot an anti-tail, a narrow spike apparently pointing toward the Sun, arising from dust distributed along the comet's orbital path. Perhaps most memorable would be its visible sweep against the stars. Most astronomical objects appear nearly motionless at night, but a bright comet moves noticeably, tracing a path through constellations and creating a dynamic spectacle, changing hour by hour. At closest approach, 3I Atlas could shift by several degrees per day, fast enough that its position would noticeably change within a single observing session. A hypothetical close pass would also open unprecedented opportunities for scientific research. Space telescopes could resolve details of the nucleus's structure and composition. Ground-based spectrographs would analyze the chemistry of gas and dust streaming off the comet. Radar observations could map the nucleus's shape and rotation state. Taken together, these data would reveal materials and processes that formed planetary systems around other stars billions of years ago. Of course, any trajectory bringing 3I Atlas this close for such observations would inevitably raise questions about impact probability. The same celestial mechanics that create a grand sky show can, with slightly different initial conditions, put the comet on a collision course with Earth. We will consider these more troubling possibilities in later scenarios. For now, a safer spectacle remains: a comet passing close enough to inspire awe, but far enough to avoid danger. The real 3-eyed Atlas will do nothing of the sort, maintaining a safe distance during its brief visit to our solar system. But it remains possible that future interstellar guests will follow more dramatic trajectories, staging displays to rival the greatest comets in human history. Part 5. How we would detect and track such a threat. The discovery of 3I Atlas began with an automated detection algorithm sifting thousands of images collected by the Atlas Survey Network. Each frame captured a small patch of sky, usually about 30 square degrees, with sensitivity sufficient to detect objects as faint as magnitude 19 to 20. Software compared new images to reference frames taken weeks or months earlier, flagging anything that shifted or changed brightness. Most detections ultimately proved to be main belt asteroids, their smooth motion betraying membership in the vast population orbiting between Mars and Jupiter. Others are near-Earth asteroids on more eccentric paths that occasionally bring them close to our planet. But several detections each year show something else: objects moving so fast across the sky that they can only be visitors from far beyond the realm of planets. The global network that makes these discoveries possible has grown sharply over the past decade. Atlas operates telescopes in Hawaii, South Africa, and Chile, scanning the visible sky every few nights. Pan-STARRS surveys from Hawaii with greater depth but a slower cadence. The Catalina Sky Survey operates from Arizona, focusing on near-Earth asteroids but occasionally finding more exotic visitors. The Zwicky Transient Facility in California combines high speed with good sensitivity, making it especially effective at catching fast movers. When any of these surveys flags a potentially interesting object, the data quickly go to the Minor Planet Center in Massachusetts, which serves as the global clearinghouse for asteroid and comet discoveries. Automated systems there compute preliminary orbits and determine whether urgent follow-up is needed. For objects with potentially hazardous trajectories, alerts go out within hours to observatories worldwide. NASA's Planetary Defense Coordination Office, PDCO, established in 2016, coordinates the US response to asteroid and comet threats. PDCO works with international partners through the International Asteroid Warning Network and the Space Mission Planning Advisory Group to ensure precise tracking of hazardous objects and timely warnings to authorities for effective response. But the current system has significant limitations. Most ground-based surveys can observe only on clear, dark nights, losing about half of potential observing time to weather and daylight. Objects approaching from the direction of the Sun remain essentially invisible until they have already passed closest approach to Earth. And surveys are biased toward detecting larger, brighter objects, potentially missing smaller but still dangerous impactors until they are uncomfortably close. The next few years will bring serious improvements to this detection network. The Rubin Observatory in Chile is ramping up to full science operations with its 8.4-meter telescope and 3.2 gigapixel camera. It will survey the entire southern sky every few nights with unprecedented depth, using advanced software designed to identify moving objects and link observations separated by days or weeks. Early modelling shows that Rubin may detect from a few to several dozen interstellar objects per year, depending on their sizes, distributions and activity levels. The fast cadence and high depth make the observatory especially well suited to finding fast movers that could be missed by surveys with longer revisit intervals. Equally important is the development of new linking algorithms that can connect observations of the same object even with large time gaps. Traditional techniques require capturing an object on at least 3 nights within a relatively short window. But advanced algorithms like Helio-Lindsay 3D can link observations separated by months or even years, essentially mining archives for objects that were observed but not recognized. These computational advances have already borne fruit. The Thor algorithm identified tens of thousands of previously unknown asteroids by reanalyzing archival survey data with modern linking methods. As Rubin begins generating terabytes of astronomical data every night, similar approaches will surely uncover many more objects hidden in the vast stream of observations. The space component of planetary defense is also progressing. NEO-Surveyor, a dedicated infrared telescope designed to find and characterize near-Earth asteroids, is scheduled to launch no earlier than late 2027, with NASA committed to launch no later than June 2028. Operating from a gravitationally stable orbit near L1, NEO-Surveyor will conduct continuous observations without interference from weather or daylight. Infrared observations offer unique advantages for detecting asteroids. Many that appear faint in visible light glow brightly in thermal emission, easing detection and characterization. NEO-Surveyor will be especially effective at finding dark asteroids approaching from the Sun's direction, closing a major gap in current ground-based surveys. The combination of Rubin's optical surveys and NEO-Surveyor's infrared observations should dramatically improve our ability to identify potentially hazardous objects years to decades before impact. But detection is only the first step in planetary defense. Once an object is found, precise orbit determination becomes critical for assessing impact probability and planning potential deflection missions. Modern orbit determination relies on a statistical least squares approach that finds the trajectory best matching all available observations while accounting for measurement errors. For newly discovered objects, the initial orbit is often highly uncertain and represented as an error ellipse that can span millions of kilometers around the predicted future position. As observations accumulate, the uncertainty ellipse shrinks rapidly. This improvement follows predictable mathematical patterns, allowing astronomers to estimate how many observations are needed to reach a given level of accuracy. For most objects, a few weeks of tracking suffice to reduce positional uncertainty to manageable levels, but some cases require special attention. Objects on nearly parabolic or hyperbolic orbits, such as long-period comets and interstellar visitors, pose particular challenges for orbit determination. Their high speeds and short observing windows mean that small early errors can grow into large uncertainties in their future positions. This statistical framework for managing these uncertainties has been developed over years of work with potentially hazardous asteroids. When an object is first found on a trajectory that may intersect Earth, it typically receives a 1 on the Torino scale, indicating it merits routine monitoring but does not warrant immediate alarm. As observations accumulate and the orbit is refined, the Torino rating usually drops to 0 as the impact probability becomes negligible. In some cases, however, an object retains a significant impact probability even after extensive observations. Such cases receive higher Trina ratings and trigger more intensive monitoring efforts. The European Space Agency maintains a continuously updated risk list, a catalogue of objects with non-zero impact probabilities, tracking how those probabilities evolve as new observations appear. The most famous example of this process concerns the asteroid 9994 to Apus, which briefly reached level 4 on the Torino scale in 2004, when initial observations indicated a small but significant chance of Earth impact in 2029. Subsequent observations, including radar measurements that precisely fixed the asteroid's position and rotation state, ruled out a 2029 impact and reduced the probabilities of later collisions to essentially zero. International coordination becomes critically important when dealing with objects that may pose a real threat. The International Asteroid Warning Network provides a framework for sharing observations and coordinating follow-up campaigns. The Space Mission Planning Advisory Group works on the more complex task of coordinating international responses to confirmed threats, including decisions on deflection missions and impact mitigation strategies. Recent planetary defense exercises have highlighted both the strengths and the weaknesses of today's coordination mechanisms. The Biennial Planetary Defense Conference includes detailed tabletop exercises in which participants work through hypothetical impact scenarios, making decisions on observing campaigns, deflection missions, and civil protection measures under realistic time pressure and uncertainty. These exercises consistently show that early detection yields the greatest range of response options. An asteroid or comet discovered decades before impact can be deflected, with relatively modest velocity changes applied at the right time and place. Objects found only months or years before impact require much more aggressive intervention, with higher mission costs, greater technical risks, and less certain outcomes. The expanding network of survey telescopes and improved orbit determination methods are steadily pushing discovery timelines earlier. Current surveys routinely find near-Earth asteroids years to decades before their close approaches to Earth. Future infrastructure, such as the Rubin Observatory and NEO Surveyor, should extend this early warning system to smaller and more challenging objects, including interstellar visitors that arrive with little advance notice. But challenges remain. Objects approaching from the Sun's direction will always be difficult to detect before they pass perihelion. Very dark objects can remain invisible to optical surveys until they are uncomfortably close. The enormous data volumes generated by next-generation surveys will require continued advances in automated analysis to avoid missing important discoveries amid routine detections. The story of 3 Atlas illustrates both the capabilities and the limitations of current discovery networks. The object was found promptly as soon as it became bright enough for ground-based surveys. Follow-up observations quickly established its interstellar origin and safe trajectory. But had that same object been on an impact course with Earth, we would have had only a few months of warning to organize any response. This timeline underscores the importance of continued investment in survey capacity and international coordination mechanisms. The universe contains countless objects moving on trajectories we cannot predict. Our ability to detect them early and respond effectively will determine whether future encounters with guests from the stars remain scientifically interesting or become existentially dangerous. Part 6. How big is bad? The difficulty of communicating asteroid and comet risk to the public led to 2 complementary scales that translate complex celestial mechanics into simple numerical assessments. The Torino scale, named for a 1999 conference in Italy, provides a simple rating from 0 to 1, combining impact probability with expected consequences. The Palermo scale offers a more sophisticated logarithmic measure that compares specific threats with the background risk from all possible impacts. Most newly discovered objects begin life at level 1 on the Torino scale, meaning current observations allow for the possibility of impact, but it is extremely unlikely. This rating triggers routine monitoring without special alarm. As additional observations refine the orbit, the vast majority of objects drop to Torino 0, meaning impact is ruled out or reduced to a practically negligible probability. Only a handful of objects have ever reached higher Torino ratings, and none have sustained levels above 4 for long. The European Space Agency maintains a continuously updated risk list, tracking all objects with non-zero impact probabilities. That list typically contains several dozen entries, from small asteroids with minuscule chances of impact to larger objects with somewhat higher probabilities. The list changes daily as new observations either remove objects entirely or push their impact probabilities up or down. Understanding these risk scales requires accepting the statistical nature of impact forecasts. When astronomers compute that an asteroid has a 1 in 10 chance of striking in 2087, they're not making a definitive prediction about that specific year. Instead, they are quantifying their uncertainty about the object's exact trajectory based on current observational data. That uncertainty predictably shrinks as observations accumulate. An asteroid discovered today might have a positional uncertainty of several thousand kilometers when projected 50 years ahead. But each additional night of data typically narrows that error ellipse by a factor of 2 to 10, depending on measurement quality and time baseline. The background impact rate provides critical context for assessing specific threats. Statistical analyses of craters and atmospheric entry events suggest that kilometer-class objects strike Earth roughly once every 500,000 to 1 million years. Smaller but still significant objects 100 to 500 meters across may arrive perhaps once every 10,000 to 100,000 years. These numbers are long-term averages. Actual intervals vary widely due to the stochastic evolution of orbits. Catalogue completeness becomes a critical factor in risk assessment. Current NASA surveys have found more than 90% of near-Earth asteroids larger than 1 kilometer, meaning we have likely identified most objects capable of global catastrophes. But completeness drops rapidly at smaller sizes. Perhaps 25% of 300-meter asteroids remain undiscovered, and the share of unknown objects rises sharply for even smaller sizes. Long-period comets and interstellar objects pose special challenges for risk assessment. These visitors come from far beyond the planetary realm on trajectories that cannot be predicted in advance. Current statistical models suggest that long-period comets might strike Earth once every few million years, whereas interstellar impacts might occur once every 10 to 100 million years. But these estimates carry huge uncertainties because so few such objects have been observed. Differences in speed between asteroids and comets strongly affect impact outcomes. Long-period comets typically arrive at 50 to 60 km per second, compared with 17 to 25 km per second for most near-Earth asteroids. Because kinetic energy scales with the square of speed, a comet delivers roughly 6 times more energy than an asteroid of the same mass. Combined with their generally lower density, comets still carry about 30% more kinetic energy per unit diameter than rocky asteroids. This speed advantage makes comets particularly worrisome despite their relative rarity. A 500-meter comet arriving at 55 km per second delivers roughly as much energy as a 600-meter rocky asteroid at 20 km per second. The comet's higher speed more than compensates for its lower density, creating significant destructive potential in a relatively small package. Interstellar objects such as Oumuamua and 3I Atlas add another layer of uncertainty to risk. Calculations. Their encounter speeds can reach 70 km per second and higher, depending on their trajectories relative to the solar system's motion through space. At such speeds, even relatively small objects carry enormous kinetic energy. A 100-meter interstellar object can deliver 200 to 400 megatons on impact, comparable to a 200-meter main-belt asteroid. The challenge for planetary defense specialists is that impact consequences scale non-linearly with object size and speed. Doubling the diameter increases destructive energy eightfold at constant density. Doubling the speed quadruples the energy. These relationships mean the boundary between regional and global catastrophes is surprisingly narrow. Current research suggests that objects in the 300 to 500 meter range mark a threshold where local and regional effects begin to merge into broader consequences. Impacts of this size can trigger multi-year climate effects if they inject sufficient dust into the stratosphere, especially if the target geology is rich in sulfates that amplify atmospheric loading. Traditionally, the 1 kilometer threshold was considered the dividing line between regional and global catastrophes, but newer climate models suggest this boundary may be lower at high impact speeds or with unfavourable target geology. A 750-meter comet hitting a carbonate platform could produce more severe climate effects than a 1.2-kilometer asteroid striking crystalline rock, because of differences in impact speed and the chemistry of ejected material. These scaling relations set today's planetary defense priorities. Objects large enough to cause global catastrophes are rare and mostly catalogued. Objects too small to do significant harm are numerous, but not worth exhaustive surveys. The focus is on intermediate sizes that combine substantial destructive potential with realistic detectability and deflectability. Future survey programs such as the Rubin Observatory and NEO Surveyor will push detection capabilities towards smaller and more diverse populations of potentially hazardous objects. These facilities should discover thousands of new near-Earth asteroids in the 50 to 500 meter range, providing a far more complete picture of mid-scale impact risk. But statistical forecasts based on current knowledge suggest that the risk to any individual's life from asteroid or comet impacts remains extremely small, roughly comparable to the risk of being struck by lightning. The task of planetary defense is not managing high-probability events, but preparing for low-probability scenarios with potentially catastrophic consequences. Risk assessment mathematics provides tools to think systematically about such low-probability, high-impact cases. Yet math alone cannot capture the full complexity of how human societies may respond to impact threats, or how international cooperation might evolve under the pressure of a potential catastrophe. We carry these questions forward by exploring concrete scenarios that could unfold if objects like the three-eyed Atlas arrived on collision courses. Part 7. Impact of the three-eyed Atlas. Part 1. Mechanics and immediate destruction. Impact physics begins the moment our hypothetical three-eyed Atlas enters Earth's atmosphere at 55 kilometers per second. At that speed, the comet's nucleus compresses the air ahead of it to pressures above 100 atmospheres, heating the gas to temperatures comparable to the Sun's surface. The object's leading edge begins to vaporize almost immediately, creating a dazzling plasma sheath visible from space. For our analysis, we consider two scenarios that span the range of possibilities suggested by early observations of the real three-eyed Atlas. Variant A assumes a 500-meter nucleus delivering on the order of 14,000 megatons of kinetic energy. Variant B scales to a 3-kilometer nucleus carrying more than 3 million megatons. Both scenarios assume a typical cometary composition, with a density of 0.6 grams per cubic centimeter and an impact angle of 45 degrees to the vertical. The 500-meter case corresponds to what planetary defense specialists call a regional catastrophe. The object would likely fragment while traversing the atmosphere, with some pieces reaching the ground and others exploding at various altitudes. The combined effects of airbursts and surface impacts would devastate an area roughly the size of a small country, with severe but survivable consequences for the broader region. Dynamic pressure on entry determines whether the object survives to crater formation or breaks up in an airburst. Pressure scales with air density in the square of speed, peaking at altitudes of 20 to 40 kilometers depending on entry angle. Weakly bound cometary nuclei typically begin fragmenting at dynamic pressures of a few 100,000 pascals, roughly 3 atmospheres. A 500-meter cometary nucleus would likely break into dozens of fragments in the final seconds of flight. The larger shards could reach the surface at several kilometers per second, excavating craters from a few 100 meters to a few kilometers across. Smaller pieces would detonate at different altitudes, producing a string of airbursts whose overlapping shock waves batter the impact region. The aggregate crater from all fragments would likely be 10 to 12 kilometers in diameter, encircled by a zone of heavy destruction, extending 50 to 100 kilometers from ground zero. The primary fireball would vaporize everything within the first few kilometers, generating temperatures above 5,000 degrees Celsius. Thermal radiation from the fireball would ignite fires over hundreds of square kilometers, while the shock wave would level most structures within a 30 to 50 kilometer radius. Case B, the 3-kilometer object, represents a fundamentally different class of event. An object of that size would likely survive atmospheric passage largely intact and strike the surface, while retaining most of its cosmic speed. The resulting crater will be 60 to 90 kilometers across, comparable to well-known impact structures such as Barringer Crater in Arizona, but enlarged in area by roughly 1,000 times. The excavation phase will unfold in roughly 2 minutes, beginning with the formation of a transient cavity about 150 kilometers wide and 30 kilometers deep. Shock waves will fracture bedrock over an even larger area, while the expanding fireball vaporizes millions of tons of target rock and cometary material. A significant fraction of this vapor will be injected into the atmosphere on ballistic trajectories, eventually falling back to Earth as a global layer of impact deposits. The choice between a continental and an oceanic impact site dramatically affects the immediate consequences. A continental strike maximizes dust injection into the atmosphere, but limits the geographic extent of instantaneous destruction. An oceanic strike spreads primary effects over a much wider area by generating tsunamis, but may inject less dust into the stratosphere. Ocean impacts create cavity collapse patterns that depend strongly on water depth. In deep ocean basins, the primary strike generates a transient cavity in both the water and the underlying seafloor. The cavity walls collapse inward, generating a complex pattern of waves that propagate outward at speeds of about 200 meters per second in deep water. These waves retain energy over vast distances, slowing and growing in height only as they shoal onto continental margins. Coastal impacts combine the worst features of both scenarios. The primary blast excavates both seafloor and water, producing giant local tsunamis that surge onto nearby shores within minutes. At the same time, the strike generates atmospheric effects comparable to continental impacts, including dust injection and thermal radiation capable of igniting fires hundreds of kilometers away. A 500-meter object scenario will likely generate tsunamis with initial wave heights of 10 to 50 meters, depending on the impact location and seafloor geology. These waves lose energy as they traverse ocean basins, but can still reach distant coasts several meters high. Coastal zones within 1,000 kilometers of the strike will face severe flooding, while more distant shores may experience waves comparable to major storm surges. A 3-kilometer scenario will produce truly catastrophic tsunamis with initial heights potentially exceeding 100 meters. Their passage across the ocean will bring destructive waves to every coastline in the impact basin, with arrival times from hours to half a day depending on distance and bathymetry. Even coasts 10,000 kilometers away may see waves 10 to 20 meters high, sufficient for large-scale destruction in low-lying areas. Atmospheric effects begin immediately after impact as the fireball rises and expands. The primary thermal pulse will be visible from space, briefly outshining the sun when viewed from the impact hemisphere. This intense radiation will ignite fires over vast areas, with the radius depending on atmospheric clarity and fuel availability. The shockwave arrives minutes later, propagating at supersonic speeds and gradually weakening as it spans larger territories. At distances of 100 to 200 kilometers from a 500-meter impact, overpressure will still be sufficient to damage buildings and injure people caught outdoors. A 3-kilometer scenario will create destructive shock waves, hazardous at ranges beyond 1,000 kilometers. Perhaps most important for long-term consequences, both scenarios inject enormous quantities of comminuted rock into the stratosphere. A 500-meter case may loft 10 to 100 billion tons of fine particulates, whereas a 3-kilometer strike injects more than 1 trillion tons. This material will begin affecting global climate within days, initiating the early stages of an impact winter that could last for years. The immediate human response will depend critically on impact location and existing infrastructure. Coastal strikes will trigger large-scale evacuations as tsunami warnings spread along threatened shorelines. Continental strikes will overwhelm regional emergency services and require national or international assistance for effective response. Communications networks will likely suffer serious disruptions within hundreds of kilometers of the strike, complicating coordination of relief efforts. Transportation infrastructure, airports, seaports, and major highways will be damaged across wide areas. Power systems will fail both from direct damage and from severe load swings as populations struggle to cope with the unfolding crisis. These immediate effects are only the beginning of a much longer chain of consequences that will reconfigure human civilization and Earth's climate system. We will trace these long-term effects in subsequent scenarios, examining how societies might adapt to a world transformed by a visitor from interstellar space. Part 8. The 3I/ATLAS Impact. Part 2. Atmosphere, Climate, Biosphere, and Human Systems. The injection of huge masses of pulverized rock into Earth's stratosphere triggers a cascade of atmospheric changes that will reshape global climate for years to decades. Fine silicate dust particles 0.8 to 8 micrometers in size are especially effective at blocking sunlight while remaining suspended above most weather systems. These particles settle slowly under gravity, but stratospheric winds distribute them worldwide within weeks of the impact. Recent analyses of the Chicxulub boundary layer suggest that fine dust can remain aloft for 15 to 20 years after a major strike, with peak concentrations lasting 5 to 8 years. In the first 2 years, the dust load may be sufficient to nearly shut down photosynthesis globally. Even our more moderate scenarios inject enough material to produce significant atmospheric effects. A 500-meter case may keep 10 to 100 billion tons of fine debris in the stratosphere, enough to reduce global insulation by 10 to 50% for several years. Agricultural regions will face shortened growing seasons and yield declines even without a complete photosynthetic shutdown. A 3-kilometer scenario may inject more than 1 trillion tons of material, potentially reducing surface sunlight by 70 to 90% in the first year and causing an almost complete failure of photosynthesis worldwide. Climate modelling suggests that near-surface temperatures will fall by several degrees Celsius within months of the impact, with the strongest cooling in the first year when dust concentrations peak. Cooling will be most pronounced over continental interiors, whereas the oceans cool more slowly due to water's high heat capacity. This temperature contrast will alter atmospheric circulation patterns, potentially disrupting monsoon systems on which billions of people depend for agricultural productivity. Target geology plays a decisive role in the composition and persistence of stratospheric aerosols. Impacts into sulfate-rich sedimentary rocks release vast masses of sulfur dioxide, which combines with water vapor to form sulfuric acid aerosols. These particles persist even longer than silicate dust and add additional cooling by interacting with incoming solar radiation. Oceanic impacts add water vapor to the stratospheric load, but the net climate effects remain uncertain. Water vapor acts as a greenhouse gas, potentially offsetting some of the cooling caused by dust and sulfates. However, water vapor is also involved in complex atmospheric chemistry that can enhance or suppress the formation of other aerosols. Current models suggest the dominance of dust and sulfate effects, with substantial regional variations depending on circulation patterns. The biosphere's response to prolonged darkness and cooling follows predictable patterns based on studies of past mass extinctions and nuclear winter scenarios. Organisms dependent on photosynthesis face the most immediate threats, whereas species able to survive on stored energy or alternative food sources have better short-term prospects. Marine ecosystems will experience cascading effects as photosynthetic collapse kills phytoplankton, the base of oceanic food webs. The collapse propagates up trophic levels. Fish, marine mammals, seabirds, though some deep-sea communities reliant on chemical energy rather than photosynthesis may remain largely unaffected. Coastal ecosystems will face additional stress from impact-generated tsunamis that scour shoreline habitats and deposit debris far inland. Terrestrial ecosystems will show strong selectivity by feeding strategies and metabolic requirements. Large herbivores dependent on fresh vegetation will face immediate food shortages, whereas small omnivores and detritivores may thrive amid abundant dead plant matter. Hibernators and species with low metabolic rates gain survival advantages during the initial crisis period. Forest ecosystems will likely collapse within the first year as trees die from lack of light and accumulated stress. Mass mortality will release huge quantities of carbon dioxide as decomposition outpaces the diminished capacity for photosynthetic carbon uptake. This release may partially offset cooling from stratospheric dust, creating complex feedback loops that are difficult to predict precisely. Human agricultural systems will face unprecedented challenges as global crop yields decline. A 500-meter scenario may cut global food production by 20 to 50% for several years, creating acute shortages but potentially manageable through rationing and international cooperation. A 3-kilometer case may halt open field agriculture entirely in the first year, forcing humanity to rely on stored food and protected growing environments. Controlled environment agriculture, including greenhouses and indoor farms, will become critical to sustaining food production during the impact winter. These systems can operate independently of natural sunlight using artificial lighting, albeit with sharply increased energy demands. Societies with substantial CA infrastructure will have significant advantages in ensuring food security. Cold-hardy crops and reserves of preserved foods would become strategically important resources. Root crops, grains, and other species capable of tolerating shortened growing seasons could continue to yield reduced harvests even under partially darkened skies. Traditional food preservation methods, including drying, fermentation, and cold storage, would extend the usefulness of warehouse stocks. Industrial systems would face major disruptions as energy consumption spikes for heating and artificial lighting, while supply chains falter due to transport difficulties and resource shortages. Electric grids would struggle to meet surging demand while also facing reduced output from solar installations and weather-related damage to wind and hydroelectric systems. Fossil fuel combustion would increase dramatically, potentially accelerating the return toward normal atmospheric composition, but at the cost of higher carbon dioxide emissions. Public health consequences would extend far beyond the immediate effects of the strike. Respiratory problems would rise as fine dust remained suspended in the lower atmosphere for months after the impact. Cold-related mortality would increase as heating systems struggle to maintain comfortable temperatures. Nutritional deficits would emerge as food diversity shrinks and caloric intake falls. Water sanitation systems would face unprecedented challenges as industrial capacity declines and energy costs spike. Contaminated water sources could spread infectious diseases among populations already weakened by cold and undernutrition. Supply chains for medical goods would be severely disrupted, hampering treatment of both routine illnesses and impact-related injuries. Recovery timelines depend strongly on the severity of the initial atmospheric load and the resilience of surviving infrastructure. In a 500-metre scenario, regional recovery might take 2 to 5 years, with agricultural productivity returning to near normal levels as stratospheric dust concentrations decline. Building codes and infrastructure planning would be revised to account for shock waves and thermal effects induced by the strike. A 3-kilometre scenario would trigger what researchers might call a dim decade of reduced insulation and global climatic disruption. Recovery would require fundamental changes in energy systems, agricultural technology, and mechanisms of international cooperation. Seed banks and genetic collections would be key to restoring ecosystem diversity as conditions gradually return toward normal. Underground facilities for data storage, power generation, and food production could prove necessary to sustain technological civilization through the harshest phases of the impact winter. These installations would require careful planning to ensure adequate life support capacity and connectivity during extended periods when the surface is uninhabitable. The human response would likely include unprecedented levels of international cooperation, as nations recognize that recovery demands coordinated global effort. Resource allocation, technology transfer, and population migration could become necessary to ensure survival in the most affected regions. The crisis could accelerate the development of resilient energy systems and closed-loop agricultural technologies that would benefit humanity long after atmospheric effects subside. Perhaps most importantly, the experience would starkly reveal the vulnerability of complex technological societies to low-probability, high-consequence natural events. Lessons learned from managing impact winter conditions could help prepare for other global challenges, including climate change mitigation and adaptation to additional natural disruptions. Recovery from a cosmic strike would reshape human civilization in ways far beyond the period of the immediate crisis. Part 9. Can we stop it? The validation of kinetic impact as deflection technique began on September 26, 2022, when NASA's DART spacecraft struck the asteroid moon Dimorphos at 6.14 kilometers per second. The collision shortened Dimorphos's orbital period around its parent asteroid Didymos by 33 minutes, showing that hitting a small asteroid with a well-aimed spacecraft can indeed predictably change its trajectory. The DART mission measured the so-called momentum enhancement factor, denoted by the Greek letter beta. This parameter quantifies how much greater the momentum change is compared to what would be expected from the spacecraft's own momentum alone. The extra momentum comes from debris ejected by the collision, acting like rocket exhaust that pushes the asteroid the other way. DART achieved beta approximately 3.6, meaning the momentum change was nearly 4 times that of a perfectly inelastic impact. This enhancement was provided by the plume of dust and rock fragments blasted from Dimorphos's surface, which remained visible to ground-based telescopes for weeks after the strike. The debris cloud effectively amplified the push delivered by the small spacecraft. But DART struck a very small target under carefully controlled conditions. Dimorphos is only about 160 meters across, and the 610 kilogram spacecraft was traveling a little over 6 kilometers per second. Scaling this technique to deflect much larger objects, as in our hypothetical three-eyed Atlas scenarios, requires careful attention to how momentum transfer efficiency depends on target properties and impact conditions. ESA's Hera mission, slated to arrive at Didymos in late, will provide crucial data to refine deflection models. Hera will map the crater created by DART and measure how the collision altered Dimorphos's physical properties. This information will help clarify how momentum transfer depends on target composition, internal structure, and surface properties. The link between object characteristics and momentum enhancement remains one of the largest uncertainties in deflection planning. Monolithic rocky asteroids may respond differently than friable cometary nuclei. Objects with substantial internal porosity can absorb impact energy without producing efficient debris plumes. Rubble piles, held together primarily by gravity, may fragment under a high-speed impactor rather than deflect cleanly. Time is the most critical factor for a successful deflection. The math is elegantly simple. A small change in velocity applied early leads to a large position shift by the time the object crosses Earth's orbit. A deflection of just 1 millimeter per second applied 1 year before impact would shift the object's position by roughly 32 kilometers at Earth's orbital distance from the Sun. To guarantee a safe flyby, mission designers typically target a displacement of at least 10,000 kilometers. Achieving that goal requires velocity changes inversely proportional to the available time. 1 millimeter per second over 10 years yields the same effect as 1 centimeter per second over 1 year, but earlier intervention takes far less energy and carries far lower risks. Multiple kinetic impactors can deliver a larger cumulative push, but with diminishing returns as the target's properties change after each strike. The first impact can create optimal conditions by cracking the surface and producing loose regolith. Follow-on strikes may be less efficient if they hit an already disturbed area or an altered geometry. The gravity tractor technique offers an alternative, especially suited to long-duration campaigns. A massive spacecraft parks near the target and lets mutual gravity slowly adjust the object's trajectory. The approach provides extremely precise control and eliminates the risk of fragmenting the target. However, it requires years or decades and thus only works for threats detected well in advance. The spacecraft must also be very massive, which may demand advanced propulsion or several coordinated vehicles. For suitable targets and timelines, such tractors can provide safer and more predictable deflection than kinetic impacts. Standoff nuclear bursts are the most powerful option for large objects or short warning times. A device detonates at a calculated distance from the target, vaporizing a thin surface layer and producing a strong rocket impulse. Modelling shows that a properly engineered nuclear deflection can change the trajectories of kilometre-scale objects by several meters per second, but nuclear deflection brings serious technical, legal, and political challenges. The Outer Space Treaty prohibits placing nuclear weapons in orbit, though planetary defense scenarios might fall under exceptions for peaceful nuclear technologies. The Partial Test Ban Treaty forbids nuclear explosions in space, creating further legal complications requiring international agreements. Technical hurdles include guidance accuracy, detonation timing, and preventing the target from breaking into many fragments that would still threaten Earth. The required precision exceeds the capabilities of any existing delivery systems. Ion beam deflection is a more speculative but potentially attractive option for very long campaigns. Focused ion streams gradually erode material from one side of the target, creating sustained thrust via reactive blow-off. It takes years or decades, but control is excellent and fragmentation risk is minimal. Advanced propulsion, solar sails, electric thrusters could unlock new, currently inaccessible methods. Mass drivers could harvest material from the target itself and expel it at high speed, generating thrust without hauling propellant from Earth. These concepts are mostly theoretical today but could become crucial for the largest impactors. International coordination for deflection missions is built on the IAWN, International Asteroid Warning Network, for threat assessment, and the SMPAG Space Mission Planning Advisory Group for mission coordination. These organizations regularly run exercises, rehearsing decision processes and identifying potential bottlenecks and collaboration delays. Recent tabletop drills highlighted the difficulty of making decisions under uncertainty and time pressure. Who has the authority to authorize a mission? What to do if deflection shifts the potential impact point from one country to another, and how to manage the risks of failure or unintended fragmentation, all remain thorny issues. Decision timelines depend on warning time and confidence in predictions. Objects found decades in advance allow for multiple attempts and course corrections. Those discovered months or a few years out require immediate decisions with minimal margin for error. In our scenarios with the three-eyed Atlas, detection would likely come only months before impact due to the high approach speed and relatively small size, drastically limiting options and demanding instant international engagement. A 500-meter case might be amenable to multiple impactors if discovered a year or more in advance. A 3-kilometer scenario would likely require a nuclear option under any realistic timelines. The success of DART proved that kinetic deflection works in practice, not just in models, but moving from demonstration to operational defense demands continued investment in surveys, deflection technologies, and international mechanisms. The mathematics of celestial mechanics give clear guideposts for what works when, but execution remains a challenge requiring sustained effort and foresight. We develop these capabilities not because an impact is inevitable, but because the alternative is unacceptable. The universe operates on timescales incommensurate with human civilizations. Yet sometimes those vast scales intersect with our brief moment on this planet. When they do, our response will depend on choices we make today, about technology development and international cooperation. Part 10. What if Oumuamua had struck instead? The first confirmed interstellar visitor, Oumuamua, had a very different profile from our three-eyed Atlas scenarios. Discovered in October 2017, already outbound from the inner solar system, this strange elongated object was estimated at roughly 100 times 30 times 30 meters, about the size of a city block, and travelled at 44 kilometers per second relative to the Sun. For analysis, we take Oumuamua as a representative 100-meter diameter sphere to simplify energy estimates. At interstellar speed, such an object would deliver roughly 190 megatons of kinetic energy upon impact with Earth. That's about 20 times more powerful than the 1908 Tunguska event, which flattened 2,000 square kilometers of Siberian forest, and nearly 400 times the energy of the 2013 Chelyabinsk bolide, whose shockwave injured more than 1,500 people. The key question for a 100-meter impactor is whether it would survive atmospheric entry and make a crater or break up in an airburst. The answer depends on internal strength, composition, and entry angle. Oumuamua's unusual elongation and tumbling rotation pointed to a coherent monolithic body rather than a loose rubble pile, favouring survival to ground impact. Entry dynamics for such an object begin at around 100 kilometers altitude, where atmospheric drag first becomes significant. The leading surface rapidly heats to thousands of degrees as it compresses and displaces air at hypersonic speeds. For rocky objects with reasonable structural integrity, the critical issue is whether dynamic pressure will exceed the object's tensile strength before reaching the ground. Dynamic pressure peaks between 20 and 40 kilometers altitude, depending on entry angle and atmospheric conditions. At Oumuamua's speed, that pressure would approach several 100,000 pascals, equivalent to roughly 3 atmospheres of differential pressure between front and back surfaces. Most rocks can withstand such pressures, but objects with significant internal fractures or weak compositional boundaries can fail under that stress. If Oumuamua survived a ground impact, it would excavate a crater roughly 1 to 2 kilometers in diameter, depending on target geology and impact angle. Immediate destruction might extend 10 to 20 kilometers from the impact point, with severe structural damage and fires ignited by the fireball's thermal radiation. The shock wave would remain hazardous to human life out to distances of up to 50 kilometers, shattering windows and damaging buildings across a much wider area. Comparison with Chelyabinsk provides useful context for these effects. That 18-meter object exploded at 30-kilometer altitude with an energy release of about 500 kilotons, producing a shock wave that damaged thousands of buildings and injured more than 1,500 people with glass fragments. Those injuries occurred despite the high-altitude airburst, demonstrating how even elevated explosions can cause widespread damage via atmospheric shock propagation. Scale Oumuamua's energy up by a factor of 400, and the destructive potential rises sharply. An airburst at 20 to 30 kilometers would create overpressures sufficient to level most buildings within 20 to 30 kilometers of the burst point. The thermal flash would ignite fires over hundreds of square kilometers, while the shock wave would cause structural damage and injuries at distances beyond 100 kilometers. Unlike our larger three-eyed Atlas scenarios, an Oumuamua-scale strike would produce minimal global climatic effects. The object simply lacks the mass to inject significant dust into the stratosphere. Local and regional smoke from impact-driven fires could create temporary downwind cooling, but it would disperse within weeks or months as the atmosphere mixed and aerosols thinned. The regional footprint of impact would depend strongly on impact site and local population density. A hit on a major megacity could produce casualties in the millions, primarily from structural collapse and fires rather than direct impact effects. Economic consequences would propagate globally via disrupted supply chains and financial markets, but physical effects would remain confined to the immediate impact region. Rural impacts would cause far fewer immediate human losses, but could still trigger significant secondary effects. Major transport infrastructure, including airports, seaports, and highway interchanges, could be knocked out by impacts at ranges of hundreds of kilometers. If shock arrival timing coincided with critical operations, power grid failures could cascade across broad regions as transmission lines and generating stations suffered damage. Agricultural impacts would vary by season and geography. An impact during harvest could destroy crops over thousands of square kilometers via fires and shock damage. Livestock losses could reach into the millions if the strike occurred in major ranching regions. Yet these losses would represent local, not global, food security problems. The entry itself would create spectacular visual effects visible over hundreds of kilometers. At Oumuamua's high speed, the bolide would be extraordinarily bright, potentially outshining the sun for observers within several hundred kilometers of the path. It would be visible in daylight for several minutes before impact, appearing as a dazzling streak across the sky, accompanied by sonic booms audible at great distances. Seismic effects would extend the impact signature far beyond the immediate blast zone. A ground impact of 1,190 megatons would generate earthquake-like shaking, with magnitudes reaching 6 to 7 on the Richter scale, within 100 kilometers of ground zero. This seismic energy would trigger landslides in mountainous terrain and could cause structural damage to buildings already weakened by the atmospheric shockwave. The psychological toll could prove no less significant than the physical damage. Unlike earthquakes or severe weather, which occur with some regularity and predictability, a major asteroid strike would be an unprecedented disaster type for modern human civilization. The sudden appearance of a blinding daytime bolide followed by mass destruction would strain existing emergency response structures and planning assumptions. Recovery timelines would be measured in years rather than decades. Unlike the global climatic disruption possible in larger impacts, an Oumuamua-scale event would allow normal agricultural and industrial activity outside the immediate impact region. International aid could flow freely to affected areas without the constraints imposed by global food shortages or climate disturbances. The event would likely catalyze major improvements in planetary defense systems and international cooperation frameworks. A demonstrated strike from interstellar space would provide unambiguous evidence that such events are a real, not merely theoretical threat. Funding for detection systems and deflection technologies would almost certainly surge in the years following such an impact. Insurance and reinsurance markets would face unprecedented challenges in assessing and pricing the risks of future space impacts. Current actuarial models lack a historical basis for estimating the probabilities and consequences of asteroid impacts. An Oumuamua-scale event would supply the first modern data point for such assessments, likely driving significant changes in how societies prepare for and respond to low, probability, high-consequence natural events. Building codes and infrastructure planning would be revised to account for shock waves and thermal effects from potential future strikes. Critical facilities, including hospitals, emergency services, and communications networks, might be hardened against blast effects or relocated to reduce vulnerability to cosmic impacts. The scientific value would be enormous, providing direct measurements of impact processes now studied only through computer models and geological evidence of ancient craters. High-speed cameras and seismic networks would capture detailed data on crater formation, shockwave propagation, and debris distribution patterns. But the human cost would be measured in lives disrupted and communities destroyed rather than civilizational collapse. An Oumuamua-scale event would represent a regional catastrophe comparable to major earthquakes or volcanic eruptions, severe and tragic for those directly affected, yet manageable within existing international disaster response capacities. The contrast with larger impact scenarios underscores the importance of early detection and deflection capabilities. Objects around 100 meters remain hard to find until they're relatively close to Earth, providing limited time for deflection attempts. Yet they are also small enough that kinetic deflection missions remain technically feasible with current or near-term capabilities. The real Oumuamua passed safely through the inner solar system and returned to interstellar space, carrying away answers about the composition and structure of materials formed around other stars. Its brief visit showed that interstellar objects do reach the inner solar system, and future visitors may not follow such benign trajectories. We prepare for the possibility that the next Oumuamua may be aimed more directly at our world. Part 11. Law, Ethics, and Geopolitics of Extreme Choices. The legal framework governing planetary defense operates within a complex web of international treaties, written without the specific challenges posed by asteroid and comet threats in mind. The 1967 Outer Space Treaty establishes that space is the province of all humankind and forbids placing nuclear weapons in orbit or on celestial bodies. but the treaty's provisions on the peaceful use of nuclear technologies could allow exceptions for planetary defense scenarios. The 1963 Partial Test Ban Treaty prohibits nuclear explosions in the atmosphere, underwater, and in space, creating yet another potential obstacle for nuclear deflection missions. Newer agreements, including the Treaty on the Prohibition of Nuclear Weapons that entered into force in 2021, add further layers of complexity by banning the use or threat of use of nuclear weapons for state parties. These treaty obligations create significant legal uncertainties in scenarios where nuclear deflection may be the only viable option to prevent a catastrophic impact. International law provides mechanisms for emergency exceptions to treaty commitments, but applying such exceptions requires broad international consensus and clear evidence that the threatened harm outweighs the risks associated with breaching the treaty. The question of who has the authority to authorize planetary defense missions becomes especially complex when deflection actions could shift the impact point from one region to another. A partially successful deflection could turn an ocean strike into a continental one, or move an impact point from a sparsely populated area into a major megacity. These possibilities create deep ethical dilemmas about acceptable risk and fair burden sharing. Current international coordination mechanisms operate through the International Asteroid Warning Network for Threat Assessment and the Space Mission Planning Advisory Group for Mission Planning. But these organizations function primarily as advisory bodies without formal authority to approve or coordinate deflection missions. National governments retain ultimate authority for decisions about space missions launched from their territory or by their agencies. The time pressure inherent in impact threats could severely strain existing diplomatic processes. Traditional international negotiations move on timescales of months or years, whereas deflection missions may require launch decisions within weeks or days of confirming a threat. Emergency procedures must be created in advance to enable rapid decision-making without abandoning principles of international cooperation and consultation. Liability questions add another layer of complexity to deflection planning. If a deflection mission partially fails and shifts the impact site rather than preventing it entirely, which parties are responsible for the consequences? Existing space law places liability on launching states for damage caused by their space objects, but applying this principle to planetary defense scenarios remains untested and potentially problematic. The distribution of deflection capabilities among states creates additional geopolitical tensions. At present, only a handful of countries possess the launch capabilities needed for deflection missions, while many more countries would be affected by the consequences of an impact. This asymmetry raises questions about how deflection decisions should be made and whether states with such capabilities have obligations to act on behalf of the global community. Nuclear deflection scenarios pose the most serious legal and political problems. Nations with the largest nuclear arsenals do not necessarily coincide with leaders in space capabilities. Coordinating nuclear deflection missions could require unprecedented cooperation between nuclear-armed and spacefaring states, potentially including transfers of nuclear materials or weapons-related technologies that are normally prohibited by non-proliferation treaties. The dual-use nature of deflection technologies creates further concerns about militarization and arms control verification. Kinetic impactor spacecraft designed to deflect asteroids could, in principle, be used against satellites or other space objects. Nuclear devices developed for deflection missions could potentially be adapted for weaponization. International monitoring and verification systems would be required to ensure that preparations for planetary defense do not become a cover for weapons development. Public communications about deflection decisions must balance the need for transparency against the risk of unnecessary panic. Officials will have to explain complex risk assessments and technical trade-offs while maintaining public trust in the decision process. Experience from the COVID-19 pandemic showed both the importance and the difficulty of maintaining clear communications during global emergencies. Different cultural and religious views on risk acceptance and technological intervention may complicate building international consensus. Some communities may regard a deflection attempt as an inappropriate interference with natural or divine processes, while others may view a failure to attempt deflection as unacceptable negligence. These philosophical differences can influence both domestic political support and international cooperation. The economic implications of deflection missions will likely dwarf the cost of any previous space projects. A comprehensive deflection campaign involving multiple spacecraft and international coordination could cost hundreds of billions of dollars and require industrial mobilization comparable to major wartime efforts. Decisions about cost and resource allocation will have to be made under extreme time pressure and with incomplete information about mission requirements and probabilities of success. Insurance and financial markets will face unprecedented risk management challenges associated with both potential impacts and possible failures of deflection missions. Current catastrophe insurance models lack frameworks for assessing global-scale risks or the efficacy of technological interventions. The interconnected nature of the modern economy could amplify financial disruptions far beyond the immediate physical effects, whether from impact or from deflection attempts. Regional security issues may complicate deflection efforts if impact threats coincide with existing international tensions. Military capabilities needed for deflection missions may be viewed with suspicion by potential adversaries. Although the coordination required for effective deflection may be hard to achieve among states with strained diplomatic relations, the precedent set by a first major deflection mission would have long-term consequences for future planetary defense. Efforts. Successful international cooperation could strengthen mechanisms for addressing other global challenges, whereas failures or disputes could undermine future cooperation precisely when it may be even more critically needed. Environmental considerations add another dimension to deflection decision-making. Nuclear deflection missions would involve detonating nuclear devices in space, potentially creating radioactive debris that could affect spacecraft operations and space exploration for years or decades. The environmental costs of deflection must be weighed against the consequences of allowing impacts to occur. The question of democratic participation in deflection decisions poses fundamental challenges for representative democracy. The technical complexity of impact risk assessment and deflection planning makes it difficult for non-specialists to evaluate proposed courses of action. Yet the global consequences of these decisions imply they cannot be left entirely to technical experts and government officials. International law provides some guidance through principles of state responsibility and international cooperation. But the concrete application of these principles to planetary defense scenarios will likely require new treaties or agreements designed specifically for impact threats. The window for crafting such agreements may be limited, since the urgency associated with real impact threats could preclude lengthy deliberation over legal frameworks. The ethical framework for evaluating deflection decisions involves balancing risks, benefits, and uncertainties across multiple dimensions, including technical feasibility, international law, environmental consequences, and fair burden sharing. These decisions will likely have to be made with incomplete information and under tight time constraints, creating situations in which moral clarity is particularly hard to achieve. We examine these dilemmas not because they are abstract philosophical puzzles, but because future deflection missions will demand international cooperation on unprecedented scales under conditions of extreme urgency and uncertainty. The legal and ethical frameworks we establish today will shape how humanity responds when the next visitor from space follows a trajectory that threatens rather than merely intrigues. Part 12. A future in which the sky is watched. Turning planetary defense from a science fiction concept into an operational capability began with the painstaking work of sky surveys that scan the heavens every clear night, cataloguing the motions of both familiar and strange objects. Today, as automated telescopes capture images of distant asteroids and rare visitors from interstellar space, we stand on the threshold of unprecedented awareness of our cosmic environment. The Rubin Observatory in Chile now combs the southern sky with its 8.4-metre mirror and 3.2 gigapixel camera, producing a detailed census of moving objects across the solar system. Each night brings terabytes of data processed by algorithms able to distinguish main belt asteroids, near-Earth objects, and rare visitors from beyond the planetary realm. Deep, rapid surveys of these facilities should detect interstellar objects weeks or months earlier than previous generation instruments, providing critically additional time for tracking and characterization. NEO Surveyor, scheduled to launch in late 2027 or early 2028, will add space-based infrared observations to complement ground-based optical surveys. Operating from the gravitationally stable L1 Lagrange point, this dedicated telescope will detect asteroids and comets approaching from the Sun's direction, closing a major blind spot in current detection capabilities. The combination of ground-based optical surveys and space-based infrared observations should dramatically improve our ability to find potentially hazardous objects years before they pose immediate risks. The success of the DART mission in 2022 confirmed kinetic deflection as a practical technique for altering asteroid trajectories. When the DART spacecraft struck Dimorphos at over 6 kilometers per second, it shortened the small asteroid's orbital period by 33 minutes and created a debris plume visible for weeks. The measured momentum enhancement factor of about 3.6 exceeded expectations, showing that carefully targeted impacts can efficiently transfer momentum to asteroid targets. ESA's HERA mission will arrive at the Didymos system in late 2026 to conduct a detailed forensic examination of the DART impact site. HERA will map the crater created by the collision and measure how the impact changed Dimorphos's physical properties, spin state, and internal structure. This information will calibrate computer models used to design future deflection missions, turning deflection from an experimental technique into an engineering discipline. But technology alone is not enough for successful planetary defense. The international coordination frameworks established through the International Asteroid Warning Network and the Space Mission Planning Advisory Group provide mechanisms for sharing observations, coordinating follow-up campaigns, and planning joint responses to confirmed threats. Regular exercises and simulations help identify potential failure points and develop procedures for rapid decision-making under pressure. The mathematical reality of deflection remains elegantly simple. Small changes in velocity applied early produce large changes in position by the time an object reaches Earth's orbit. A deflection of just 1 millimeter per second applied 10 years before a potential impact yields a position shift of roughly 320 kilometers at Earth's orbital distance from the Sun. This scaling strongly favors early detection over last-minute intervention, making continued investment in survey capabilities the most cost-effective approach to planetary defense. Future deflection missions will likely apply multiple techniques depending on the specific characteristics of threatening objects and the available warning time. Kinetic impactors perform well for strong targets discovered years or decades in advance. Gravity tractors provide precise control for long-duration deflection campaigns. Standoff nuclear bursts offer high-energy options for large objects or short warning times, albeit with substantial legal and political complications that must be addressed through international negotiation. Developing rapid response characterization missions using small satellites and rideshare opportunities will enable detailed study of newly discovered threats within months rather than years. Understanding an object's composition, structure, and spin state becomes critical for designing effective deflection missions and predicting their outcomes. Advanced propulsion systems, including ion engines and solar sails, may allow these missions to reach targets faster and operate longer. The expanding catalogue of near-Earth asteroids inspires growing confidence that we've identified most objects capable of causing global catastrophes. NASA surveys have found over 90% of kilometre-scale near-Earth asteroids, meaning unexpected impacts large enough to trigger mass extinctions have become extremely unlikely. But completeness drops sharply at smaller sizes, and the discovery rate of city-killer objects in the 50 to 500 metre range continues to accelerate. Long-period comets and interstellar objects pose ongoing challenges due to their unpredictable arrival times and high approach speeds. Current statistical models suggest these events are rare on human timescales. Yet their high kinetic energies make them potentially dangerous even at relatively moderate sizes. Improved survey capabilities should provide earlier warning for most such objects. However, some approaches from the Sun's direction may remain hard to detect until they pass their point of closest approach. Lessons learned from managing the COVID-19 pandemic highlighted both the importance of international cooperation during global emergencies and the difficulty of sustaining coordinated responses across different political systems and cultural contexts. Planetary defense scenarios will likely require even higher levels of cooperation due to the technical complexity of deflection missions and the global nature of impact consequences. Public education about asteroid and comet risks remains key to building support for investments in planetary defense and ensuring rational responses to future impact threats. The dramatic yet low probability nature of cosmic impacts makes them hard to communicate without causing either undue alarm or dangerous complacency. Understandable risk scales, such as the Torino scale, help translate complex celestial mechanics into accessible threat assessments. The economic benefits of planetary defense extend beyond catastrophe prevention and include scientific discovery, technological development, and frameworks for international cooperation that are valuable in their own right. Asteroid characterization missions provide insights into solar system formation and the distribution of potentially valuable resources. Deflection technologies, advanced propulsion systems, and high-precision navigation methods applicable across space exploration. Climate change and other environmental challenges have shown humanity's capacity for outstanding technological innovation, alongside frustrating political stagnation in addressing long-term global problems. Planetary defense presents similar challenges but with more favorable political dynamics due to the clearly external nature of the threat and the unambiguous benefits of successful intervention. The story of the Three-Eyed Atlas illustrates both current capabilities and remaining limitations of planetary defense systems. We promptly detected this interstellar visitor, characterized its basic properties, and confirmed a safe trajectory within months of discovery. But if the same object had been on a collision course, we would have had only limited time to organize any deflection mission. Future interstellar visitors will likely be discovered earlier as survey capabilities improve, offering more time for characterization and potential deflection if needed. A combination of ground and space-based surveys, improved linking algorithms, and rapid response campaigns should lengthen warning times and improve our understanding of these exotic guests from other stellar systems. Developing planetary defense capabilities represents one of the few areas where human technological progress directly addresses existential risks that have shaped Earth's history for billions of years. Large impacts have repeatedly altered the course of biological evolution, most famously ending the age of dinosaurs 66 million years ago. For the first time in Earth's history, an intelligent species has developed the ability to detect and potentially prevent such catastrophic collisions. This capability carries a responsibility that extends far beyond our own species. Earth is the only known example of complex life in the universe, containing millions of species and ecosystems that have no voice in decisions about planetary defense. The choices we make about investments in surveys, deflection technologies, and international cooperation frameworks will influence the trajectory of life on Earth for generations to come. The sky, once seemingly still and predictable, has revealed itself to be dynamic and at times hazardous. Objects wander between the stars on journeys that began billions of years ago and can continue for billions more. At times, these wanderers encounter inhabited worlds, creating moments of intersection between processes on cosmic scales and the brief intervals of individual civilizations. We cannot predict when the next such intersection will occur, but we can prepare for the possibility that it will happen within the lifespan of human civilization. The tools we develop, international frameworks we establish, and the knowledge we accumulate will determine whether future encounters with visitors from space continue to inspire awe or become agents of destruction. In our imagination, two trajectories cross the inner solar system. One carries the three-eyed Atlas past Earth at a comfortable distance, the other brings a similar object into collision with our world. The difference between these paths may be measured in kilometers of space, but the consequences span the gulf between scientific curiosity and civilizational crisis. Which trajectory we meet depends on the chance dynamics of objects scattered across the galaxy billions of years ago. But our response to that encounter depends on the choices we make today about watching the sky and preparing for what we may find there. The universe is vast, ancient, and largely indifferent to human concerns, yet it is not entirely unpredictable nor entirely beyond human influence. In the precise mathematics of orbital mechanics, in the patient accumulation of observations by automated surveys, and in frameworks of international cooperation that cross political and cultural boundaries, we find the foundation of a future in which cosmic collisions become predictable problems rather than random catastrophes. The sky is watched, the instruments are ready. What remains is whether we will continue to build these capabilities with the sustained effort that planetary defense demands. The answer to that question will be written not in the stars but in our choices about technology, international cooperation, and our commitment to protecting the world that produced a mind capable of grasping its own cosmic context. We are the first generation with the ability to defend our planet against a cosmic impact. That is all we know for tonight. The sky is not a backdrop but a living system where, from time to time, something small and fast decides the fate of everything large and slow. We're used to thinking of space as a distant background, but the last decades taught us the opposite. Its processes touch us directly. And yet this knowledge brings not only cause for anxiety, but also a rare sense of responsibility. We are, for the first time, able to turn chance into a manageable task. The story of Three-Eye Atlas is a reminder that a meeting can prove harmless, but the next one may be different. In our imagination, two lines still diverge. One carries the interstellar visitor deep into darkness, the other pulls it onto an intersection with Earth. The difference between them is measured in kilometers and fractions of a second, but the consequences are the fates of cities, ecosystems, and generations. We do not choose the outcome of the cosmic lottery, but we do choose preparedness, to learn to see earlier, to calculate more precisely, and to act more in concert. The math here is comfortingly simple. A millimetre per second applied in time changes everything. This simplicity paradoxically demands complex infrastructure: mirrors, sensors, algorithms, tracking stations, and escort missions. Surveys like the Rubin program and the upcoming NEO surveyor rest weeks and months back from fate. DART showed that imparted momentum changes an orbit not in models but in reality. HERA will turn this practice into an engineering discipline. Every unit of data, every early we noticed, is additional kilometres of standoff distance we win from celestial mechanics. But technology does not exist in a vacuum. Our age is also law and ethics, treaties, exceptions, responsibility, authority. Who signs the launch order when the window's only a few weeks? What is fair if a partially successful deflection moves risk from ocean to land? How do we prevent a defensive technology from becoming an argument in other, less noble disputes? The answers must be ready in advance, before headlines, before panic, before the sound of a countdown. We will not untie these knots in urgent mode, and so the only wise path is shared rules, shared drills, and shared transparency. There is another layer, the human one. Explaining to the public a rare but high-energy threat is no easier than computing ballistics. We must speak in ways that neither inflate fear nor lull vigilance, provide clear risk scales and state uncertainties honestly. Support for surveys and missions does not appear from nowhere. It is cultivated by education, trust, and procedural predictability. Planetary defense is a project not only for engineers, but also for teachers, journalists, economists, and lawyers. It is a rare case where a common language is literally needed by everyone. Beyond our cities and arguments lies the silence in which the planet's other inhabitants live. They have no voice at briefings, but we have a duty to remember them. Earth is the only known haven of complex life, and the idea that we can shield it from the ancient statistics of impacts changes the scale of our responsibility. Perhaps this project is the bridge between generations, the proof that we includes those we will never see. In the end, this is not a story about threat, but about maturity. About how science, law, and cooperation add up to a new norm, to watch, to understand, and to be ready. About how, one night, a telescope will find a tiny point, an algorithm will link its tracks, and a group of people in different time zones will make a quiet, measured decision. If we are lucky, those decisions will always seem excessive. The object will pass by, the instruments will power down, and we will go back to our business. But that is exactly what victory looks like, when catastrophe remains a hypothesis. The sky is watched. The instruments are ready. What remains is to bring ourselves to readiness, to make coordinated action a habit, to invest in advance, and to value data more than hunches. Then, when a nameless wanderer emerges from the dark next time, we will meet it not with fear, but with work. Calm, collective, precise work. The work of a generation that, for the first time in history, managed to place between cosmic chance and the home on Earth its will and its reason.